In this video, I'm going to review some of the fundamentals of coding in R. If you've signed up for one of my intermediate or advanced workshops, these are the basic concepts, terminology, and programming techniques that I will be building upon and that I assume most people are familiar with. All of this is very standard stuff, and if you've taken any kind of R training in the past 5 years, this should all be extremely familiar. On the other hand, if you learned R a long time ago or you've never really had a solid training in R, perhaps because you self-taught yourself how to code in R through trial and error, it wouldn't be a bad idea to review this material so you can get the most out of all of the great resources for learning R that are out there. This is an outline of what I'll cover here. Feel free to use the chapter links in the description to jump to the sections that look most interesting. I'll start off by talking about the differences between R and RStudio and mention some of the other integrated development environments out there. Next, I'll review some of the terminology we use to describe R commands when you enter them at the console as essentially a fancy calculator. We'll then look at objects and classes, including some of the rules for naming objects, and then review the 4 things you need to know to use functions effectively, including how to find and import the packages that have the functions you need. Piping syntax is a way of chaining together multiple functions into something that resembles a sentence rather than a really complicated expression, which is a little bit unique to R, as are vectors and vectorized operations, which are built into the language. We'll briefly mention data classes that you can use to work with tabular data before finally reviewing why data analysts mostly do their work in scripts and notebooks. First, let's talk about R and RStudio, because these are often mixed up or assumed to be the same thing. First and foremost, R is the name of a programming language that was inspired by S and developed specifically for data analysis and statistics. R is also the name of software that you can download and install from CRAN to work with R, including writing and running scripts. R first came out in the early 2000s, so it's 25 plus years old and very mature. RStudio, on the other hand, is an integrated development environment, or IDE, which is a program that allows you to write and run R scripts, plus a bunch of other convenience functions such as managing packages, plots, data import helpers, and so on. RStudio was developed in 2016 by a company also called RStudio, now Posit, so it's a much younger program than R. Like all IDEs, RStudio requires R to also be installed because it runs R in the background whenever you execute a command. But you don't actually need RStudio or any IDE to run and write R code. There are some other IDEs that are also very popular in the R community. Posit Cloud is essentially RStudio in the cloud, which you run through a browser, and which has the same look and feel of RStudio, but with the advantage of not having to install anything locally. Positron is a newer IDE from Posit, which was developed specifically for data scientists and has gained great popularity, in part because it also supports Python. VS Code is another popular IDE that is extremely well developed and has an extension for R. A good way to get started with R is to think of it as a fancy calculator where you can enter things at the console and hit enter to see the results. So when you type an expression at the console, such as this mathematical expression here, and hit enter, R will evaluate the expression and then print the results to the console. So that's what we see here. You type an expression, you hit enter, you see the results. You can also save or assign the results of an expression to an object. So in this case here, it's the same expression, but we're saving the results of that expression to an object X. When you do this and hit enter, R does not print the value at the console. That's an important difference. R also has 2 assignment operators. So we just saw the single equal sign, basically assigning the value of that expression to object X. There's also this arrow operator, so 2 characters that together look like an arrow, which can be visually interpreted as taking the results of this expression and pushing them into the object X. So these are both assignment operators and they do the same thing, and you see them both quite a bit. To view the value of an object that you've created and have in memory, you can enter it by itself and hit enter. So here we have an object called X. You want to see what it contains. You can just enter it at the console, hit enter, and R will print out the results. Once defined, you can also use objects like X in subsequent expressions. So here, for example, we type X divided by 4 and hit enter, and R uses the value of X when it evaluates this and gives us the results 250. We can also create another object, save the value 1.2, and then use both of those objects in another expression to see the results. It's important to note though that all of these objects that we're creating, X and Y, they are stored in memory and they will disappear when you shut down R, unless you tell R or RStudio that you want to save the environment. There is a way to do that, but it's actually not a bad idea that all of your objects in memory disappear, because one of the reasons people like to use a computational language such as R, because it allows you and forces you to create scripts to save your work so that you can quickly recreate all of these objects, and therefore your work is completely reproducible. So all objects that you create have a data type or class. It's not quite obvious and you don't declare it like you do in other languages. We've already seen a number of mathematical expressions, and those create numeric objects, obviously. There's also character and factor classes. So these are both for text. Factor is text that has a lot of repeated values in it. Other functions will return dates or dates and times. Data frame, tibble, and matrix, these are all data classes for two-dimensional data that has rows and columns. And finally, list is another data class, which is a very flexible data structure for all kinds of interesting objects. Often, if you are doing more than just very simple calculator work, you will want to save or name your objects with more meaningful names than X or Y, which you might not remember when you come back to do your work. So fortunately, R has pretty flexible rules for naming objects. You can use numbers, letters, and most of the special characters. There are a few exceptions though, a few rules to remember. First of all, the first letter of an object cannot be a number. That will give you an error message. Also, you can't use spaces in your object names because R will consider that to be two separate objects. And you can't use hyphens either, because a hyphen is also the operator for subtraction or minus. So that's not a valid function name, and R will try to subtract an object called last and an object called name together, and that probably won't work. Finally, it's not a good idea to use the name of a built-in function, constant, or keyword for one of your objects. It's not an error, but there's disadvantages. So for example, there is a very nice function that comes built in. It's called C. It stands for combine. So if you create an object called C, like C equals to 7, there's nothing wrong with that, but then it means you can no longer use the combine function because you just redefined the symbol C. Likewise, cosine and pi, these are all built-in functions and keywords and constants, so it's a bad idea to use those as object names. There are a handful of popular styles for naming objects that various people use. So all lowercase is pretty popular. You simply just use all lowercase. You don't have to worry about upper and lowercase letters because R is case sensitive. So everything in R, including the names of objects, including the names of functions, you have to get the capitalization right. So if you use all lowercase, you don't have to worry about that. You can use periods in object names. That's fine. That works well. Some people do that. Other people don't like that style because periods are used other places in R as well, so that might get confusing. Snake case is where you use underscores in your object names to make it more readable. That's very common. And then you can also use upper and lower cases Again, mostly just to make your object names a little bit more readable. So I think the important thing is pick what style that you like and try to be consistent. Let's talk about functions, because functions are the key to our superpowers. There are lots and lots of really well-developed functions that can do what you need to do, but there are 4 things you need to know to use a function effectively. First of all, you need to know the function that does what you need. That might be obvious, it might not be. It might be in your base package of R that you install, it might not be. It might be something you have to install a package for. So finding the function is half the battle. Next, you need to know about the arguments. The arguments are the things that you put in parentheses. You need to know which of those are required, which of them are optional, and it's useful to know in what order they are expected. And we'll see here in a second how you find out about the arguments. But that's a really important detail that you need to know. You also need to know, what does the function return? Every function returns something. Sometimes what they return isn't important or necessary, but all functions return something or other. So you need to know, particularly if you're saving the value of that function to an object that you're going to use later on, you need to know exactly what it's returning. And then finally, some functions take actions, and some functions we use primarily because they take actions such as drawing a plot, such as writing some data to the disk, or changing other objects in your environment. So there are a handful of functions that do actions, and we use them mostly because they take actions. They are functions, they have arguments, they do return something, but we're mostly using them because they take an action. So that's another important detail. So what can functions return? Well, we've already seen functions that return numbers. There are other functions that will return dates, text, data frames, and matrices, so these 2-dimensional data structures. Some functions return spatial data, some functions draw plots and return the plots, mathematical models, and so on and so forth. Some functions return functions. Some functions are very specialized. Essentially, almost anything you can think of under the sun can be returned by a function. So this is really great because it also means that anything that is returned by a function can also be saved to an object. So you might have some really specialized object that's returned by a function, and you can save it to an object, and then you don't have to recreate it each time, the next time you want to use it. What function should I use? Finding the function is half the battle. If you know the name of the function and it's the right function for the job, then you can almost definitely figure out how to get it to work. So how do you find functions? You can ask your friends, your colleagues, you can take classes like this. If you have a general idea of what you're looking for, like you're trying to create a Fibonacci sequence, but you don't know what function would do that, you could ask Google or ChatGPT. That's often fairly effective. Google and ChatGPT, they're good resources that I turn to quite a bit. And then finally, many packages have cheat sheets, and I'm a big fan of cheat sheets. So here, for example, we're looking at some of the cheat sheets from Posit, from some of their popular packages. And if you look at some of these cheat sheets, they do all kinds of crazy things, all kinds of useful things, but you know, many of these function names you wouldn't necessarily just guess out of your head. They're kind of specialized. So cheat sheets are a really good way of finding out the names of functions that do what you're looking for. Every function has a help page. This is a requirement of R. It's also why R shines among the data science languages. When you publish a package, you are required by CRAN to create a help page for it. And these help pages are easy to find. You just type the question mark and then the name of the function, and out will open a little help page. And part of the help page is this usage section. And this usage section tells you, this is a help page for 4 related functions. It tells you the actual arguments that each of these functions requires, as well as if it has a default value. So this is really, really helpful. So if an argument can be required or optional, optional simply means it has a default value. So let's look at this, for example, sample function. We can see that there's 4 arguments: x, size, replace, and prob. Replace and prob have default values. So if you are happy with these default values, you don't have to use them. You don't have to enter them when you call the function. X and size, on the other hand, do not have default values, so these are required arguments. So that's an important detail, but it's easy to find once you get to the help page. Also, you can choose whether or not, when you write your function, whether to name your arguments. Naming your arguments simply means when you enter it inside the parentheses, in addition to the value, you add the name. So like n equals 100, mean equals 10, st equals 10. These are named arguments. So that's not always required. You can sometimes omit the names, but the benefits of naming your arguments is that it helps you remember what each argument is. You can just imagine if you just put rnorm 100, 10, 0.3, you might not remember what each of those are for, right? Where if you put in the names, then you'll remember. Another benefit of naming your arguments is you can put them in any order. It doesn't have to be the order that's expected that you saw in the help page. It also allows you to skip arguments, right? So if you're happy with one of the default values, you can just skip over those and enter just the ones that you are interested in changing or that are required. Again, that's if you use named arguments. That being said, though, if it's a function you've used 1,000 times, you can actually just omit the argument names, and here's an example of that. So rnorm generates a randomly distributed set of numbers from a normal distribution, and because I've used this 1,000 times, I know that 500 means that's going to be 500 numbers, 50 is the mean that they'll be centered around, and 3 is the standard deviation. Let's also talk about R packages. Packages are what R calls extensions or add-ons in other programming environments. And what do you get in a package? Primarily, you get functions. Packages have special use cases, and mostly what they provide you will be functions for that kind of work. All of those functions have help pages. Packages also have tutorials, which are also called vignettes, which kind of describe in plain language how you might go about using the various functions in the package, like in what order, for what kind of use case, and so forth. Some packages also come with data sets, and there's a small number of packages which primarily exist as a way to share data, right? So they may or may not have many functions, but they're bundled with data. Where do you find packages? So kind of like the functions, you got to ask around. You can ask people in your field. CRAN, the company that makes or manages the R ecosystem, have web pages called task views. So here's an example of a task view. Basically, it's a web page that has different topics that have been written by people who know this field. So for example, clinical trial design. So this is basically written by a group of authors who know a lot about clinical trial design. They work in that field, but they also are R users. And these pages are essentially an annotated bibliography of packages in that field. So that's a pretty good way to find out about functions or packages. There's also another website that you can turn to, which is a list of all packages from CRAN, of which there are I think over 20,000 at this point. So quite a long list, but you can just use Control F and try to find packages here. Sometimes publications will have packages listed in them, and then blog posts and other kinds of places online, right? So finding packages helps you find functions, and once you've got the right package, the right function, you're probably good to go. Once you know the package that you need, installing them is pretty easy. So install means you have to download it. You only do this once. So in RStudio, there's a packages pane, and then there's a big old install button. You click on there, you type in the name of the package you're looking for. If it's on CRAN, it'll pop up, and then you just install it, right? So installing a package only has to be done once, but you do have to load the package into memory each and every time you start working in R. And you do that using the library function. So that's what that means. There's one package, or more accurately, a family of packages that deserves special mention, and that is the tidyverse. The tidyverse is a collection of R packages designed for data science and focus on really common tasks such as importing data, wrangling data, visualizing, modeling, and so forth. The tidyverse packages share a common design philosophy and syntax style, which once you get the hang of it is actually quite intuitive and allows you to work efficiently through features like creating data pipelines, which we'll see here in a second. So you can install or download all of them at once. There's these 8 core packages plus roughly 10 others which are designed for importing different kinds of data. You can install all of them once by installing the tidyverse meta package, and then you can load these 8 core packages into memory all at once using the library function as before. Or of course you could load them into memory one by one, the individual packages. And to see a list of all of the packages in the tidyverse and more information about them, you can go to this link. So let's talk a little bit about piping syntax, because that is one of the features of the tidyverse packages and many other packages out there as well. So piping is a syntax for essentially writing chains of functions in an easier form. So many of us, if you've ever worked in Excel and you've had to write an equation that combines lots of functions and maybe they're nested, and you can wind up with a expression like this, which has lots of nested parentheses, and it works fine, it executes well, but it's a little bit hard to read, and if you mess up one of your parentheses, you omit one, or you put it in the wrong place, it could take quite a while to figure out. So this is kind of the problem that piping syntax was designed to address. The way it works is that you use the pipe operator, and there's 2 of them that you can use. The first one is this pipe followed by the greater than sign. There's also this other operator which you can use. This is from the Margarita package, so it's a little bit older. They do basically the same thing. And when you put functions together, when you join them using one of these operators, what it will do, it'll take the results of one function and pass them kind of automatically and invisibly to the next function as the first argument. So this allows you to take a series of commands and write them more like a sentence. The best way to understand this is to see an example. So here we have an expression, and there's 1, 2, 3, 4 functions, and they've been combined in this deeply nested expression. So with piping, we would take the first expression, right, the middle one that gets evaluated first, and then we use that pipe character and we pipe it to the next function in the chain, which is in this case boo, and that pipe character will bring it into the boo function as the first argument, which we actually don't even have to write because it's there, it goes there automatically. And then R will evaluate that, pass the results of that to the next function, which in this case is moo. And the moo function also has another optional argument, so that can be added after the first argument is emitted. And then finally we pipe that into zoo. So when all is said and done, this expression here can be rewritten like this, which is a much easier kind of way to read the function, right? So this is more like a sentence, and it's fairly intuitive to read and to write. So piping syntax allows you to create these chains, which is really useful, particularly in data science, where we're often doing where a lot of data science, data analysis, is taking a series of functions and putting them together in some kind of sequence. So that's piping syntax. Couple tricks around piping. The native pipe we just mentioned was introduced about 2 or 3 years ago, so most people are using that now. But there's also this older pipe operator from the Margarita package that you still see that quite a bit. Something else that piping allows is, and R allows, is that you can take an expression and spread it across multiple lines. So here we have a piped expression where the last character on each line, the last operator, is a pipe. So this is a good way. We see this a lot when you're working with data wrangling. A series of steps is written across with pipes across multiple lines. And if you do need, as we saw before, if you do need another argument in one of the functions, you simply enter it. But again, you don't enter the first argument, because that pipe operator will always insert the results of the previous expression as the first argument automatically. Okay, so piping is used really commonly. Another issue with functions is what happens when you have the same function in different packages, but they have the same name, unfortunately. So occasionally, two or more packages will have different functions, but they use the same name. So that becomes a problem when both of those packages are loaded. Typically, R will simply use whichever one was loaded first. So here, for example, over, right? So there's a function called over, and there's a package called SP, and then there's another package called GR devices. They're both good packages. They do good stuff, but unfortunately, they both have a function called over that do very different things. Another one is select. So to deal with this, one thing you can do is to simply prepend the name of the package using the double colon operator, right? So in other words, we're not letting R take a guess about which over function to use. We're telling it explicitly use the one from the SP package. So that's a common technique that you can use. So you package name, and then the double colon, and then the function name, and then you don't have to worry about these name clashes. Another option that you can do, if that gets tedious, is to use the conflicted package. The conflicted package is designed explicitly to allow you to, in your script, put your preferences for which package to use when an ambiguous function is encountered. And here's an example of doing that, right? So basically, this function here is saying, from here on out, whenever you see the filter function, use the one from dplyr and not some other random package. All right. So there's two ways to deal with package name or function name clashes. Vectors are another feature that is somewhat unique to R, whereby many objects have the ability to store not just one value, but multiple values, provided they're all of the same class. So in this example here, we see we're creating a object called I, and it contains the sequence of integers from 4 to 12. So it's one object, I, but when we hit I at the console and hit enter, we see it actually contains 9 different values. And this is built into R. We didn't have to do anything special. Here are some other examples of objects, which are vectors, that contain examples of doubles, which are basically numbers that have decimal places, more integers, true-false values or logicals, and then characters. So we'll see here in a second why this is useful, but to make a vector, you generally have to use a function or an operator, right? We just can't type in a bunch of numbers and magically have it convert to a vector. So we just saw here the colon operator generates a sequence of integers. So that's one way that you can create a vector of integers. REP stands for repeat. So this function will also return a vector that repeats the first argument n times, where n is the second argument. So here this expression is returning a vector, a character vector, with the word quercus 5 times. There's a bunch of other functions that return random numbers. There's some built-in constants like month.name, which is also a character vector of the names of the months. And the other functions like sample will actually return a vector. It'll draw a random sample from the first argument and return that. So those are some examples of functions that return vectors. Also, you can use the C or combine function to kind of create a vector from scratch. So the C function will take the arguments that are entered kind of in a function syntax and return them as a vector. So here we're creating an object called yn, and it is a logical vector. It has three values. If you want to know like how many elements are in a vector, you can use the length function, and that'll tell you how many elements are in the vector. So here's why that's all useful, because many of the R functions and math operators are vectorized, meaning they will operate on each individual vector, which creates extremely concise code. So here, for example, in this example, we're creating two vectors, one called x, one called y. They both contain numbers. So sign is a mathematical function, and it's vectorized, meaning if you pass it a vector of numbers, it will return a vector of numbers, the signs of those numbers, assuming the numbers are in radians. Likewise, cosine and most of the mathematical functions in R are vectorized. Again, meaning you give it a vector, it'll return a vector. It'll apply the function to each and every element and return the results as a vector. Addition is also vectorized, right? So here we have x. Remember, x was a series of numbers. We're saying x plus 1. It's going to add 1 to each and every element of x, as this is the result. And you can even add two vectors together. And assuming they have the same number of elements, it'll add them element-wise. If they're not the same, it'll try to repeat to make up the difference for whichever one is shorter. So those are vectorized functions. Other functions are aggregate functions, meaning they're not vectorized. So sum is an example of a function that you pass it a vector, and it's not going to return a vector. It's simply going to add up all the numbers and return a single number, which is technically a vector of length 1, but we don't necessarily think about it that way. These are called aggregate functions. So mean, standard deviation, these are all examples of functions that take or can take a vector and will return a single value. It will aggregate them mathematically. Oftentimes, you have a vector and you want to pull out specific elements. You don't want to work with all of those elements. And in general, R uses square brackets. So you type square brackets after the name of the object, and then inside that square brackets, you put some kind of expression that's going to tell it which of the elements that you want to be returned. So we'll see some examples of that. So state.abb, that's a built-in constant. There's 50 text elements in there, the abbreviations of the US states. So if you type that and then you put in square brackets an integer, it'll interpret that integer to be the index, and it'll return, in this case, the 5th element of the vector. Right? You can also put in multiple numbers, multiple integers in the square brackets, and it'll return multiple elements. And you can also use this to get the elements back in a different order. So here, for example, we're passing inside the square brackets a vector created by the C function containing 10, 4, 6, 9, and it'll go to the vector and it'll pull out the 10th, 4th, 6th, and 9th elements and return them in that order. Right? So you can do a lot with this square bracket notation. Something else you can do, instead of using numbers inside the square brackets, you can pass true-false values, and it will return the elements where the corresponding value is true. Right? So that's another way that you can subset a vector. More frequently, instead of putting in a vector of true-false values, quite often you put in an expression of true-false values. So here's an example of an expression that's going to return true-false values, one for each element of month.name, and it has the effect of, in this case, pulling out the elements where the first letter is M, because we're using this substring function here. right? So the general point, though, is that there's ways that you can pull out specific elements of a vector. Let's talk about tabular data. Tabular data is really common in data analysis. It's basically any kind of data structure that's divided into rows and columns. So R has two main data classes for this kind of data: data frames and matrices. You may have also heard of tables. Tables are basically the same as data frames for all intents and purposes. Depending what field you're from, rows in this kind of structure could be called a record, an observation. In GIS, we might call these features. And then the columns, again, in different fields, whether economics or ecology, these might be called variables or fields. But in general, tabular data has rows and columns, and generally I use those terms to describe them. So a couple key concepts about tabular data. So if you have a data frame, each of those rows is actually a vector, meaning it's all the same type. The columns can also have names, right? So columns names, which is very handy because then you can refer to the column by its name. You can also refer to columns by their position by passing its position index. Again, that would be 1, 2, or 3, that kind of thing. And then finally, I just mentioned that data frames and tables are basically equivalent. So to get out an individual column to work with, you can use the $ operator. So here we see an example where there's a built-in data frame called trees. It has 3 columns, and if all we're really interested in working with is the height column, we can enter the word trees, $height, and it will return that column and only that column as a vector. So the values of that column are returned as a vector. And here's an example where we're piping that vector of numbers into the summary function to see the quartiles. And just like we did with vectors, you can use square bracket notation to subset a data frame. The only difference is inside the square brackets, because data frames have rows and columns, you have to enter 2 expressions separated by comma, right? So here we see the first expression inside the square brackets defines the rows that you want to return. So in this case, rows 10 through 12. And then the second expression is the columns that you want returned. And again, you can refer to them by name or by their position, their index. Importing data is a common need in working with data science. RStudio has some helper functions which are quite useful for importing data from standard database formats, including Excel and CSVs, but also statistical software, SPSS, SAS, Stata, and so forth. Another way that you can import data into R using RStudio is to find the data file in your Files pane, and then you right-click on it and choose Import Dataset, and it'll open up a wizard that will help you import the data. It'll prompt you to identify the columns that you want. It'll give you the option to identify what data type each of those columns are, and so forth. So importing data is easier than it used to be thanks to these dataset import wizards from in RStudio. Scripts are something else that we commonly use in working with data in R. So we already saw lots of examples of typing R expressions at the console and hitting enter. That works fine, but we can do the same thing and actually save our work, get more mileage out of it by putting those commands into a script. So here we're seeing an example of a script which is doing some plotting, and it's in a script window. A script is simply a text file that has R commands, and then these other lines that appear in green, these are comments, which we know they're comments because they start with the pound or hash character. So typically when we're working in programming languages or RStudio, we're going to be working in scripts. There are a lot of advantages for this. Number one, it's just easier to write, and quite often you may have to fix your code if you're working in that script window than if you're in the console. You can also add comments, as we just saw, that remind yourself what each command is doing and sort of the logic and flow of the script. So that's very good practice to comment liberally what your code is doing. It allows you to reuse your code by simply copy-pasting it and adapting it from one place to another. So scripts give you that option. You can also create loops and create if-then statements. So now with these structures, you're basically going from a linear set of commands to creating something which is more like a proper program that you can use for automation. And you can build in loops and if-then statements. That's a slightly higher programming technique, but not terribly hard. And then it's just more fun to work in a coding environment. Notebooks are similar to scripts in the sense that they are text files that have R code that gets executed when you render the notebook. They go beyond scripts, however, because when you render the notebook, the results of your code also get included in the output. You can also add formatted elements, such as headers and paragraph text, and things like figure captions and images, and table of contents, and other elements that make the output easy to read. Another nice thing about notebooks is that the output can be in HTML, PDF, Word, and a couple other formats. So they're a really good way to document your finished work so that you can share it with colleagues or your future self. Notebooks are also good for bundling up and presenting a reproducible analysis, because every time you save the notebook, each and every bit of R code gets run again, so you'll know if there's any errors. So that concludes this overview of the fundamentals of coding in R. If most of this stuff was familiar to you, you're in a good position to continue your learning journey and take advantage of all the great resources for learning R that are freely available online. If there were any concepts or terms that were really unfamiliar, you might consider exploring those pieces further by maybe asking Google or ChatGPT to explain those concepts, or perhaps look for tutorials on those topics in YouTube. As always, if you have any questions or comments, please leave them below. And if you'd like to see more content like this, please like and subscribe to the channel. Thanks, and I'll see you in class.